If you just take Newton's gravitational constant, Planck's constant, and the speed of light, and try to build from those three constants something which has the units of energy, it turns out there's only one way to combine them that gives you something with units of energy, and that defines what is the Planck energy, which turns out in units of billion electron volts to be 10 to the 19. Anyway, that's where we expect our knowledge of physics to break down. And we put in that cutoff on this calculation, we get a finite number for the vacuum energy density, but it's too large. And it's too large by 120 orders of magnitude. That's the bad thing about this. So not only are we not understanding what this vacuum energy density should be, but we are unbelievably far off from understanding what this vacuum energy should be. So that's the mystery. How did it get to be so small? I should add, I didn't say it yet, but there are both positive and negative contributions to this, and we don't know how to calculate any of them. So it's consistent with our ignorance that they might somehow cancel and give you a number that's very small, but we don't see any reason why that should happen. We have no understanding of why that should happen. And that's not what happens in string theory. What happens in string theory, and I guess I'm getting there soon, I'll get there soon what happens in string theory, so I'll stop now. In terms of our understanding, this gets combined with an idea about inflation, which I'll now tell you about, which is the idea that inflation produces not just one universe, but a whole multiverse of universes, an infinite number of universes, literally. And I'll tell you how that happens. The material that drives the inflation, which is often called a false vacuum, is a metastable material, like a radioactive substance. It has a tendency to decay. And that's, of course, what ended inflation the first time I went through the story. And it really is true that if you just sit in one place and watch what happens to this false vacuum, with a very high probability, in a short length of time, it will undergo a decay and become normal matter. But what happens, which is very strange, but if you think about it, it's almost obvious once you see somebody tell it, when somebody knows it's going to happen, while this is going on, the material is also exponentially expanding. So both are exponential. So there's a half-life to the decay and a doubling time to the expansion. And if you wait for one half-life of the decay, it does mean half of it will have decayed. But the catch is that the expansion is faster. So that if you wait for one half-life of the decay, the half that is not decayed will, at the end of that time period, be bigger than what you started with. And it will just keep doing that literally forever. We don't know of anything that will ever stop it. So this leads to a phenomenon which is referred to as eternal inflation. The word eternal is not quite accurate because we don't think it's eternal backwards into the past, which is what the word eternal should literally mean. But it's eternal into the future. It's future eternal. Once it starts, it never stops. And it produces then not just one universe, but an infinite number of universes. The volume of this false vacuum actually increases with time, even while it's decaying. And the inflation therefore becomes eternal. Once it starts, it never stops. The inflating region never disappears, but instead pieces of it undergo decay and produce what we call pocket universes. We would be living in one of those pocket universes. And that goes on ad infinitum with a sort of a substrate of this false vacuum continuing to exponentially expand forever. So instead of just one universe, you get an infinite number, and that's what's usually known as a multiverse these days. All this is fairly new vocabulary. It hasn't quite settled down yet necessarily. But there's a strong belief that this is the way almost all inflationary models behave, as far as we can tell. That's the story. It is possible, by the way, to build models that do not behave this way, so there's a small chance that this is not the way inflation behaves. But in almost all models it does, and that's what people are now pursuing. Question?
The multiverse is infinite simultaneously or infinite variant sequentially?
Okay, the question was, if you didn't hear it in the back, is the multiverse infinite immediately, or is just infinite sequentially? So if you wait long enough, an infinite number will be produced. It turns out that time is sufficiently badly defined in general relativity, so that question actually does not have quite a unique answer. Depending on how you define time, the answer could be either yes or no. Either it's immediate or takes an amount of time. But either way, the bottom line, and I think this is the right bottom line, is that if this picture is right, you produce in the end an infinite number of pocket universes. Okay, so what does that do? Well, it gets combined with other ideas coming out of string theory, and this is where string theory, M theory comes in. For many years, string theorists have tried to figure out what the vacuum of string theory is. But how does string theory describe just plain empty space? And it turns out they've never been able to do that, which is one of the embarrassments of string theory. However, within the past 5, maybe it's now 8 years, most string theorists have come to believe that it's not just because they've been dumb, it's because maybe string theory doesn't really have the unique vacuum. And that has become the current belief. They now believe that string theory has perhaps as many as 10 to the 500 very long-lived states, any one of which could act like a vacuum and could become a substrate for one of these pocket universes. And this set of possible vacua is what is referred to as the landscape of string theory. And there are several popular books now about the landscape of string theory. If that's true, then eternal inflation, which produces an infinite number of these pocket universes, can presumably produce pocket universes of all types, with all types of vacua coming out of string theory in the different pocket universes. So inflation would populate the landscape of string theory. And that leads to very strange consequences. Even though the laws of string theory would be the same everywhere, when you build the pocket universe on top of different kinds of vacua, the physics that we actually see at low energies are really just the different ways that our vacuum can be perturbed. So the low energy physics, the kind of physics that would be observed in each of these pocket universes, would really be different from one pocket universe to another. The kinds of particles that could exist would be different from one pocket to another. The way they would interact, the constants of nature, the charge of an electron, if there was anything like an electron, the mass of an electron, if there was anything like an electron, all those quantities would be different between one pocket universe and another. And furthermore, the energy density of the vacuum would be different from one pocket universe to another. So that's the situation that one has led to if one takes the latest ideas from string theory and combines them with these ideas from inflation. Now, what does that tell us about the cosmological constant? It gives us a strange answer that's possible. Now, I don't know if you should believe it or not. I won't tell you whether or not you should believe it, but I'll explain it to you. It involves an idea which has come to be called anthropic environmental selection, or it's sometimes also called the anthropic principle. Maybe many of you have heard of it. Here's the idea. Let me first give you an example where you'll believe that it works, because otherwise it sounds crazy, and then I'll apply it to the cosmological constant. Suppose, for example, we just talk about the local density of matter around us, say within a mile of us or something like that. So the sphere, a mile around us, and ask what's the average density of matter in that sphere. It'll be something on the order of a gram per cubic centimeter if you're in this room, I assume. On the other hand, if you ask what is the average mass density of the universe, I think most people aren't aware of how empty the universe is, but the average mass density of the universe is actually only about 10 to the minus 30 grams per centimeter cubed. Unbelievably thin. So the place where we're living is extraordinarily dense compared to the average. So let me pose the question, why is this so? Why is it that we happen to be living in a place that's so unusual? Why aren't we living someplace typical in the universe, where the mass density is close to the average, 10 to the minus 30 grams per centimeter cubed? Why did we just happen to find ourselves in this unbelievably dense place? Is it chance? Is it luck? Is it divine providence? Well, I think most of us would probably say that it's none of those. It's probably a selection effect. It is probably life only forms where the matter density is in one of these collected states. We certainly expect that this kind of collection of matter will happen. That's not a surprise. But if you look at any one place, you don't expect to find it. The average is going to be 10 to the minus 30. And places where the mass density is high are incredibly rare. But still, we might believe that life only evolves in those rare regions. We believe that life doesn't form in the centers of stars. It doesn't form in intergalactic space.